Okay, it's time to get started. 12 o'clock high. We either got to lecture or hang somebody. So I suggest we go ahead and lecture, unless we have any volunteers. If the lecture is bad enough, sometimes I get volunteers. That's just a little joke. Okay, so we're working on pumping systems, and I think this is where we left off. We'll do some of this, and we'll jump back and forth to PSAT and measure some today. But so we want to talk a little bit about parallel and series pumping systems and how we would work with those in doing an analysis. And so I think just for clarity, I was looking around for some images. I don't have images on all of this stuff, but there is, I think I got some images of parallel. Here we go. This little Zoom thing messes stuff up sometimes. Okay, but so this is what we mean by parallel pumping. So we've got a big pipe down here that is the suction that provides the supply of fluid to the pumps. This would be called a suction header, H-E-A-D-E-R, and they all pull out of this. And then, you know, each pump does what it can, and it pushes the fluid up into a discharge header. So that's collector here, but they're really called headers. And notice we have a pressure. You typically have a header pressure gauge, and the plant will usually know what kind of pressure they have to maintain here in order to be able to supply all of the users that are downstream. So this can be a big pipe. This could be 10, 12, 14, 16, 18 inches, and these could be very large pumps. This could be like a cooling water loop that's going to a bunch of machines that have to have water, they have to be water cooled. Air compressors are sometimes water cooled, and just all sorts of heat transfer furnaces, and arc welding equipment sometimes has to be water cooled, and there's lots of reasons. Lots of manufacturing equipment has to have some sort of a cooling, and water cooling is usually more effective for the heat transfer than air cooling. And if you air cool it, you wind up dumping the heat in the plant a lot of time, and that's not good because it's already hot in there in the summertime, and here you are dumping all the air compressor heat out into the plant. Everybody, it's, you know, uncomfortable and ticked off and all that sort of thing. So water cooling is common. This could be supplying to a cooling tower. Water falls across a cooling tower. We dump, you know, 8, 10, 12 degrees of temperature out of it and then send it back out to the plant, pick up more heat, come back, dump it to the cooling tower, and it just circulates around. This shows how we can combine pump curves. I will do some more on this from the presentation, but I wanted to show you that. And while I'm already out, let me go ahead and show you what series pumping. We'll be talking about that next. So series, we just have, this shows 2 pumps in series. So, you know, we come in the first one will boost pressure a certain amount, and then that same flow goes into a second pump. So it boosts pressure a certain amount, and you can have any number of these things in series. And then, so basically these, you get a pressure boost for the same flow every time you go through in series. Okay. So now that we got some pictures of that out there, let's go back to this. Let's see. Okay, so in terms of, and this is thinking about combining, like if we had 2 or 3 pumps in parallel, how would we draw an equivalent pump curve for 2, 3, 4 pumps? And so basically, the theory says that for parallel pumps, you sum the flow rates at a given head, or given pump head. And we'll see this. And then for series, we sum the heads at a given flow. Okay, so you keep that in mind. Okay, and so this would be for if we had 3 identical pumps that were running in parallel, we see this first curve over here would be the single pump curve. So this is what comes from the manufacturer. You know, he tells you, or maybe you've adjusted it for a different operating speed, but probably not. This is probably just what came from the manufacturer. And so if I'm going to run two pumps in parallel, what I do is I pick a bunch of these different heads. For example, I pick 140, and whatever the flow is here, I multiply it by 2. And so that puts me out, and this becomes a point on the 2 pump in parallel curve. If I run 3 in parallel, guess what? I take this single pump flow at whatever head and multiply by 3. And so then that takes me right out to here. And, you know, if I'm doing 4, I multiply it by 4, and I come out to here, and 5, I come out to here, and 6, I come out to here. And that just gives me 1 point on each one of those equivalent pump curves. And then I come down at 120, and I do the same thing. So I pick whatever this flow is, you know, 5, I don't know, 6,000, you know, whatever you would read it to be, multiply it by 2. I get another point on the 2 pump curve, and then multiply it by 3, and I come out here, multiply it by 4, multiply it by 5, however many pumps I'm operating in parallel, I just keep, and then, so I do this all the way, probably from this point all the way up to, you know, someplace in here, and then this point obviously is 0. They all have that in common. And then I just draw smooth lines through those points, and so then I have a curve for 1 pump, for 2 pumps, for 3 pumps, however many I wanted to draw. And I do that in Excel, and I've got my equivalent pump curves. And then I put my system curve on that. I just have one system curve. And wherever the system curve crosses each one of those lines tells me where I would operate with 1 pump, 2 pumps, 3 pumps, 4 pumps, however many pumps I want to turn on. That's kind of how we go through the analysis. And we'll see more of that here shortly. Okay, now that was with 3 identical pumps. But what if I have 3 different pumps? Because, you know, you go out there in the real world and it's never that simple. Like, well, we had 3 identical, but this one crapped out. And we had this old one back here in the storeroom, and it was still a good pump. No, it's not quite the same as the others, but, you know, it's kind of close. So we said, what the heck, we're just going to use it. And then one of the other 2 crapped out, and they said, oh, we got this big one down here from this other plant, and they gave it to us for nothing. And nothing's a whole lot better than paying $20,000 for a new one. So they said, well, just put it in there. Well, let's run it and see if it works, you know? So, I mean, stuff happens. You probably wouldn't design it like this, but, you know, you might have to analyze one. So, well, what do? Well, it's the same theory, but you have to realize that, for example, this pump number 1, what is that, about 110, is its shutoff head. If the pressure it's trying to discharge into is greater than this, it's not strong enough to push any fluid out. And so it's what we call deadheaded, and it's basically a water heater. And if you run it real long, all that energy can't escape from the pump, and you're going to vaporize the fluid, and it's going to start boiling in there, and eventually you're going to tear up the pump, okay? So with pump number 1, you'd have to be real careful that you had some protection, or you tell the operators, hey man, if that system pressure is over about 100 feet, don't turn it on. It's not going to help you, and it's just going to sit there and use energy. Okay, now, if you're down here at you know, 80, 85, 90 feet, okay, then it can produce some flow. Okay, so you've got, there's the curve for pump 1, there's the curve for pump 2, and the dotted line is the curve from pump 3. Okay, well, we can start up here at high heads. Up here at 140, guess what? Pump number 3 is the only one that's strong enough to produce any flow. Okay, so if you start at its shutoff head is 160, so from 160 down to about 120, about what is that, 132, 133, down to here, the combined total pump curve is just the curve for pump 3, because it's the only one that's strong enough to, the others, if you turn them on, they're pushing, oh, but I'm not strong enough. It's like me trying to bench press 400 pounds. I can push all day long, but I'm not going to move it. It's not going to work. Now, when you start getting down into here, say 130, 125, 120, all this, well, pump number 2 can start to produce some. And so you have to take that portion of the curve, like say at 120, I would take this amount for pump 2, this amount for pump 3, add